All right, so I believe at the end of last class, we worked problems 1 and 2 from that in-class assignment, but we didn't get around to problem 3. So we're going to knock out problem 3 here, just for the sake of having more practice on these power relationships. Then we're going to get into our power factor correction stuff. So for this particular problem, we are told that we have a balanced three-phase source is powering 3 loads, one of which is drawing 24 kilovolt amperes of apparent power at a power factor of 0.6 lagging. We have a second load that's drawing 10 kilowatts of average power at a power factor of 0.75 lagging. And then we have an unknown third load. We are told the line voltages at the load is 208 volts RMS in magnitude at 60 hertz. We are told the total apparent power absorbed by the composite load is 35.52 kilovolt amperes, and the power factor at which our source is supplying power is 0.88 lagging. And we are asked to determine the average power absorbed by load 3 and the power factor at which load 3 is absorbing power. So effectively, it's very similar to the work that we've done previously, except that now I tell you what the source is doing and I'm making you work backwards to find out what one of the loads is doing. All right. So do you guys have any thoughts on how we might approach this problem? Yeah, pretty much exactly right. So let's figure out what our source is doing, right? So this is the complex power supplied by our source. And so that's going to be simply our apparent power with an angle of the inverse cosine of the power factor of our source. And so that would be 35.52 angle inverse cosine of 0.88. And this calculator is set to give me answers in rectangular, which I hate. All right, so we get 35.52 angle 28.358 degrees kVA. So for load 1, that's going to be the apparent power drawn by load 1 with an angle of the inverse cosine of power factor of load 1, which is going to look like 24 angle inverse cosine of 0.6 which I get to be 24 angle 53.130 degrees kilovolt amperes, and the complex power absorbed by load 2. Here we were given average power, not apparent power. So we're going to have to do average power of load 2 divided by the power factor of load 2 with an angle of the inverse cosine of the power factor of load 2, which would be 10 kilowatts divided by 0.75. inverse cosine of 0.75. Or 13.333 with an angle of 410 degrees. So from here, I'm going to do exactly what Brock has suggested. I can say that the power of load 3 is simply the power supplied by our source minus the power absorbed by our loads. So if I stored things in my calculator correctly, this comes out to be 13.088 with an angle of negative 58.403 degrees kilovolt amperes. And I'm going to choose to express this one in rectangular as well. So that would be 6.856. Excuse me, 858 minus J 11.148 kilovolt amperes. So for part A of this question, we were asked to determine the average power absorbed by load 3. So which of these four numbers is the average power? The real part of the rectangular representation. Absolutely. So this guy right here tells us that P for load 3 is 6.858 kilowatts. How do we find the power factor at which load 3 is operating? Cosine of which angle? Yeah, so this guy right here, the negative 58.403. So the power factor for load 3 is the cosine of negative 58.403 degrees. Which I get to be 0.524. Is this leading or lagging? Leading. Why? Exactly right. Negative angle. You guys are getting to where it is a Pavlovian response when I ask that question, which is great. I don't want you to have to think about it. I want it to just be in your head. Great. All right. So this problem involved us effectively doing the same stuff that we've been. So I am pleased. Okay. So any questions about this one before we move on to today's topic of three-phase power factor correction? All right. So this will be power factor correction in three-phase systems. So this is incredibly similar to power factor correction in a single-phase system, like we've previously learned, except that now we're going to be dealing with capacitor banks instead of just individual capacitors. Okay. So imagine, if you will, over here on the left-hand side, I have a balanced three-phase source. It does not matter if this is connected in Y or delta. We will always have access to transmission line terminals A, B, and C, like so. Over here, I'm going to put a balanced three-phase load. And once again, it will not matter whether it is connected in Y or delta. I will have access to transmission line terminals capital A, capital B, and capital C. And I'm going to connect my source to my load with just a wire. I'm not going to worry too much about line impedance here, although it wouldn't be that hard to sort out how that's going to work anyway. Okay, so when we were dealing with single phase power factor correction, we simply placed a capacitance in parallel with our voltage source. So that is the exact same thing that we're going to do here, but now we have an option. We can either connect our capacitor bank in a Y configuration, or we can connect our capacitor bank in a delta configuration. Okay. So effectively tapping into my A line, I would place some capacitance, which I'm going to call CY, between A and some arbitrary neutral terminal. Now, I want to be very, very clear here that this neutral terminal in my capacitor bank does not have to be connected to a neutral terminal in my source or my load, because those literally may not exist. This is just me tying one terminal of all of those capacitors together to form what's behaving like a neutral node. Okay. So there's the A phase. Here's the B phase. And here's the C phase. All three of those capacitors have the exact same value, CY. So this is my Y-connected capacitor bank. And our other option would be a delta-connected capacitor bank, which I'll put over here on the right-hand side. So for our delta-connected bank, we would put a capacitance C delta between the A and B transmission lines, between the B and C transmission lines, as well as between the C and A transmission lines. So all of these guys are C delta. So the hardest part about dealing, and let me label this. This is my delta capacitor bank. The hardest part of dealing with three-phase power factor correction is, one, remembering that in our equation for power factor correction, let me write that down here. We know that C was supposed to be equal to, bless you, P old times the tangent of theta old minus the tangent of theta new divided by the magnitude of the voltage drop across our capacitor squared, right? That was our single phase equation for determining the value of the capacitor. We're going to use this exact same equation, except that we need to make a couple of quick notes here. So this P old is a single phase power. We need to make sure, even in a three-phase power factor correction system, that we are using the single phase power. And so the reason for that is because we're not correcting the power of all three phases with a single capacitor. It's literally impossible. We're correcting the power on each phase. So that's why we're using a single phase power. So this power right here is just going to be P three phase divided by 3. Okay. So if we can figure out the three-phase power, divide that by 3 to get the power per phase, and that's what's going to go into our P old relationship. The voltage VC is the voltage drop across our capacitor. That voltage is going to be different if our capacitor bank is connected in a Y or if it's connected in a delta. We know that they're related to each other by √3 as far as magnitudes go. So we just need to pay attention, okay? So this could be a VL or VP, just depending on how our source is connected and or which type of capacitor bank that we're using. Okay. So with those two things in mind, we've effectively covered three-phase power factor correction. It is identical to single-phase power factor correction, except that we need to make sure that we just use one phase of our average power, and we need to pay special attention to the voltage drop across our capacitor. So we're ready to work problems. So let's look at ICA number 10. Okay. And just as a heads up, I brought a textbook that has a ton of questions in case you guys want more practice with this after we knock out the ICA. I'm perfectly okay with that. So in this first problem, we have a balanced three-phase source supplying a balanced three-phase load. Notice nowhere do I tell you if anything is connected in Y or delta. Our load is drawing power factor of 0.8 lagging. The line voltages at the load is 4.6 kilovolts RMS at 60 hertz. And I ask you to determine the size of the capacitors needed to correct the power factor to 0.95 lagging if the capacitor bank is connected in a Y configuration and then a delta configuration. All right, so I'm going to write down our equation for C here. So this is going to be P three-phase times tangent theta old minus tangent theta new divided by 3 times omega times the voltage drop across our capacitor squared. So this little modification right here lets me keep the three-phase power, and it's going to divide it through by 3 for me. Okay. So let's talk about what pieces of information we have and which pieces of information that we can very easily solve for. Okay. So How would we solve for P3 phase based on the information that's provided here? I don't think that we do have P old. What do the units of volt amperes mean, Zach?
I'm thinking of the wrong field. We can find, yeah.
We can. I'm asking you how to do it.
Billable on that. And your 60 hertz and. That'd be 125.
All right, so you've given us something there. Not what I'm asking for, but it is useful. You told me that omega is going to be 120 pi, the linear frequency of operation 60 hertz. Now, I would argue that we don't have enough information to calculate P3 phase from the voltage because that would require us to know an impedance or it would require us to know a current, and we don't know either of those things. So there's got to be a different way to do it. Baylor, you have any thoughts? How have we done it in every other problem like this, where we are given the apparent power or average power that a load draws in the power factor? We literally just did this 3 times in the last example problem. So tell me how to do it again. If you have to look at the last example problem to figure it out, that's okay. Yeah, so this 20 MVA right here is the apparent power drawn by our load, which is the same thing as the apparent power drawn by our source, since nowhere was it mentioned that we have any particular transmission line impedance, right? So I would argue that S 3-phase old is 20 megavolt amperes with an angle of the inverse cosine of 0.8. Which I get to be 20 angle 36.870 degrees megavolt amperes in polar form and 16 plus J12 megavolt amperes in rectangular form. So using that information, what is our 3-phase average power? 16 megawatts. So it's just the real part, but we need to make sure that we use the unit of watts or megawatts in this case to differentiate between the average power and the other types of power that we might be seeing. All right, so we figured out P3 phase. We figured out omega. So all that's left is theta old, theta new, and the voltage drop across our capacitor. We're going to do the voltage drop across our capacitor last because that's going to depend on whether or not we are in a Y configuration or a delta configuration. So let's sort out theta old and theta new. So how are we going to figure out theta old? I'll give you a hint, we already have it. Yep. So theta old is the 36.870 degrees that we got when we calculated the complex power supplied by our source. Exactly right. So we are told that we are correcting the power factor to 0.95 lagging, so we simply take the inverse cosine of 0.95 lagging. Thank you. Which I get to be 18.195 degrees. All right, so now let's start with part A. We have a Y configuration. Okay. So CY is going to be 16 megawatts. That's our average power for our three-phase system, multiplied by the tangent of 36.870 degrees minus the tangent of 18.195 degrees, all divided by 3 times 120 pi radians per second. And now we need the magnitude of our voltage. Okay. So up here in the problem statement, we are told that the line voltage at the loads is 4.6 kilovolts RMS. So what I want you guys to sort out is what the phase voltage across our Y-connected capacitor bank will be. Will it be 4.6 kilovolts RMS? Or will it be 4.6 kilovolts RMS divided by the square root of 3? So we are given line voltage. Let me draw a picture here. Or actually, let me go back to the picture that I've already drawn right here. Okay. So we're talking about our Y-connected capacitor bank. We were given the line voltage, which is measured between the transmission line terminals. We were not given the phase voltage measured between the transmission line terminal and our neutral, right? So we are effectively having to convert this delta voltage into a Y voltage, which is done by dividing by the square root of 3. Okay. So if we come back over here, this would be 4.6 kilovolts RMS divided by root 3 squared. Now I want you guys to notice something here really quickly. What's the square root of 3 squared? 3. So I believe that I have a 3 in the numerator of my denominator and a 3 in the in the denominator of my denominator, and those guys are going to wind up canceling each other out. So 3 divided by root 3 squared is just 1, right? So this is what our CY is going to be. So let's throw this into our calculator really quickly. So 16 times 10 to the 6th So I'm converting my megawatts into watts times the tangent of what I have stored in my calculator as X minus the tangent of what I have stored in my calculator as Y divided 120 pi times 4.6 times 10 to the 3, converting my kilovolts back down to volts squared. I get 845.047 microfarads. So we have a couple of different ways to solve for the delta really easily. What is your suggestion for really easily, Brock?
Well, like it's what? So
It is.
it's like
100% right. So I'm going to write all that down, and then we're going to talk about a couple of things here. So 16 megawatts tangent 36.870 degrees minus tangent 18.195 degrees, all divided by 120 pi times 3 times 120 pi times 4.6 kilovolts RMS quantity squared, which comes out to be 281.682 microfarads. I want you guys to do me a favor. I want you to take that number for CY and divide it by the number that we got for C delta. What are we going to get? 3. Why do we get 3? So up here, I had 3 and then divided by √3 squared, which is like 1. Here I have 3 and not dividing by the √3 squared. So it's literally the exact same expression divided by 3. Does that make sense? I hope it does, because this is nothing more than a delta Y transformation on our load. However, I want you guys to pay a bit of attention here, because typically speaking, the impedance of a delta connected load is divided by 3 to get our Y connected load, right? We're not dealing with impedances here. We're dealing with the capacitor values. Because we know that the impedance of a capacitor is inversely proportional to the capacitor value. So the impedance of a capacitor is 1 over j omega c. That's why it appears to go backwards here. Okay. So going from the delta connected to the Y connected is multiplying by 3 when we're dealing with just the capacitor value itself, but our impedance is actually being lowered by a factor. All right. Power factor correction. Nothing wildly difficult. If you have any questions about this one, I'd be happy to answer them before we move on to our second problem. Okay, so in this guy, we have a 3-phase Y connected source that is supplying power to a Y connected load, which consumes 50 kilowatts of power in each phase at a power factor of 0.8 lagging. 3 capacitors are found that have an impedance of negative J2 ohms at whatever our system's operating frequency is. And I want us to determine the power factor of the combined load. So by that, I mean the load and the capacitor bank together. If the capacitors are connected in a Y configuration or a delta configuration. So this is a similar problem to the last problem from our last ICA, where we're using our relationships kind of backwards in order to sort things out. All right, so I want to employ an approach that is similar to what we did with the last problem of our last ICA. So effectively, what I'm saying is that S three-phase for our source should just be S three-phase for our load plus S three-phase for our capacitor bank. So the source is providing enough power to provide whatever the load and the capacitor bank are absorbing. Are we okay with that? Cap for capacitors. So I feel pretty strongly that we have enough information to figure out what the complex power absorbed by our load is. So I would like for you guys to tell me how we might go about doing that. So that would be the complex power absorbed by each phase. How would we get the total? Multiply it by 3. Absolutely right. So S
It's what we covered last class. I don't know why.
yeah, so we don't have any currents, so we can't really use that one in particular. Okay. So we have average power. We don't have the impedance of our load at all. We only have the impedance of our capacitor bank. So we have our average power here, which is the power per phase. We also have the power factor. So we are doing literally the exact same crap that we've been doing for a month at this point. If we know average power and we know power factor, that's all we need to know to get complex power. Okay. So this will be 3 times 50 kilowatts over 0.8 with an angle of inverse cosine of 0.8. Which I get to be 187.5 with an angle of 36. Why do I have that 3 out in front again? We need to account for all 3 phases. Absolutely correct. Okay. So now we need to figure out how to determine our complex power absorbed by our capacitor bank. So what do we know about our capacitor bank? We know its impedance. And that's really, it's not it, but it's pretty darn close, okay? So I'm going to draw a picture here. I'm sorry, I can't hear you over there. What were you saying? Where do you see that the load only has an imaginary impedance? The capacitor bank has an impedance of negative J2. The load's impedance, we do not know. Yep. Let me give myself enough room here. Oops. Oops. So I'm drawing our transmission lines as if they have no impedance because there wasn't one mentioned. We could. I mean, that's literally what we did there.
Yeah, I'm in.
Using the single phase equivalent circuit and all that kind of stuff. For this one, we could, in as much as we are told specifically that our source is connected as a Y and our load is connected as a Y. But in our previous example, we were not told how any of our connections were made, so we can't really use a single phase equivalent circuit for that. Okay. So this is what we have. This is our impedance ZY. We literally do not know what it is. I argue that we could find it out if we wanted to, but it's not really going to be useful for us, so I'm going to leave it alone. Okay. So in part A, we're trying to find the power factor of the combined load if the capacitors are connected in parallel in a Y configuration or a delta configuration, right? So part A is the Y configuration, part B is the delta configuration. So I'm going to put my capacitor here in blue. So this is ZCY. This is that same ZCY. And this is that same ZCY. So what's the voltage drop across my capacitor? Yeah, absolutely. right? So I would argue for part A here that the complex power absorbed by our three-phase capacitor bank is going to be 3, because there are 3 of them that we're going to be, or 3 capacitors that we're going to be dealing with, times the magnitude of VAN squared divided by the impedance of our capacitor conjugate. This is a relationship that we learned when we were covering single-phase circuits, where the complex power absorbed by any generic impedance could be expressed as just the magnitude of the voltage drop divided by the conjugate of the impedance. If you want me to derive it again, it'll take 20 seconds, but hopefully we've used this one enough to where we know it's where it's coming from. The factor of 3 here is just because we have a 3-phase system. Okay. So from my problem statement, I know that the voltage drop across my capacitor is 220. So that's going to be 3 times 220 squared. What's the conjugate of my capacitor's impedance? Positive 2, or positive J2, yeah, so 2. And so I get 72.6 angle negative 90 degrees kVA. So we now need to figure out the complex power of our combined load. So that being our load itself plus the capacitor bank. So we're simply going to add those guys together, right? So let's call that S 3-phase total is just S 3-phase, what did I call this up here? L plus S 3-phase cap I get 155.216 with an angle of 14.896 degrees. kVA. What's the power factor of my combined load? Cosine of the angle, right? So cosine 14.896 degrees. Or 0.966, leading or lagging? Lagging. See if that checks out. Seems legit. Okay. So I'll let you guys write all that stuff down. You can ask any questions about it if you want before I erase it and we go on to part B, just because I don't have enough space, I don't think. Sure.
Way that the capacitor is it's just like an ELET.
Yeah. Yeah, because I have a Y connected capacitor bank for part A. It explicitly says determine the power factor of the combined loads if the capacitors are connected in parallel with the load in a Y configuration or a delta configuration, right? So now let's work on the delta configuration stuff. So I'm going to erase these Y connected capacitors. So power factor divided by 3 doesn't mean anything. So the power factor of a single phase system and the power factor of a 3-phase system are literally computed in the exact same way. It's just the cosine of the angle of the total impedance, or the ratio of the average power to the apparent power. So the reason why we're going to have to make significant changes here is because, like I mentioned earlier, when we put our capacitor bank in a different configuration, the voltage drop that the capacitor sees is going to be appreciably different, and that's going to make us change things. You know? So if I here, so if I were to connect my capacitor bank in delta, I'd be placing it between my transmission line terminals like so, right? So here is C delta, C delta, and C delta. Actually, these should be ZC deltas because we are given an impedance, right? We're going to use effectively the exact same equation to determine the complex power absorbed by our capacitor bank. So that's going to be 3 times the voltage drop across that C delta thing, whatever it is. I'm just going to leave it as a V for right now, and we'll sort it out in a moment, divided by ZC conjugate. But now we need to figure out what that voltage is going to be, or at least what the magnitude of that voltage is going to be. Does anyone have any thoughts? It is exactly what would be VAB. So how would I get VAB from VAN? Other way around. Times √3, yeah. So this is just going to be, the magnitude of our voltage is just going to be 220 √3. So the magnitude of what we would have is VAB squared, which, just as a heads up, is going to be 9 times what we had as the magnitude of VAN over ZC conjugate. So it's effectively just 3 times as much absorbed power. So 9 times 220 squared over 2I comes out to be 217.8 angle negative 90 degrees kVA S 3-phase total load plus S 3-phase cap or 183.270 with an angle of negative 35.069 degrees. And now our power factor is the cosine of negative 35.069. Which comes out to be 0.818 leading or lagging. Leading because the angle was negative. So a vastly different power factor because we connected our capacitor bank in a different way. Okay. So let me ask you guys a question. Which configuration here, based purely on the impedance that we were given, does a better job of correcting our power factor? Y connected gets us closer to 1. Both of them technically correct our power factor in as much as the power factor changed from 0.8 to a number that's greater than 0.8. But the Y connected configuration happens to get us much closer. So let's talk very briefly, and I want to go back to the prior example problem here, where we weren't keeping the impedance constant, we were finding our capacitor values here, right? So in this previous example here, we calculated the particular capacitor value needed to get us to a target power factor if our capacitor bank was connected in Y, and then we made the same calculation if our capacitor bank was connected in delta. Obviously, we can use a delta connected configuration or a Y connected configuration for power factor correction. So why might we want to use one over the other? You guys have any thoughts? So we can see here very clearly uses a capacitor that is literally 3 times larger than the delta connected capacitor bank. What are the implications of that capacitor is larger? It might cost more. I say it might because there's also something else that we need to take into consideration, okay? So the delta connected capacitor is smaller in capacitance value, but it has to be rated for a larger voltage because it sees the line to line voltage versus the line to neutral voltage, right? So realistically, it's going to be cost that's driving everything as to whether you use a delta connected capacitor bank or a Y connected capacitor bank. While a smaller capacitor may be cheaper, it's also a smaller capacitor that's rated for a higher voltage. So it's not a simple, this one's going to cost less. We need to pay attention to that as well. All righty. So we've got 45 minutes left. What do you guys want to talk about?
The day that we talked about what the consumer sees and that load being either passive or inductive changes, what you need to do. And I know we've never done any correction on inductive load.
No, you've got it backwards. The only thing that we have done is correction on inductive loads. We have never corrected a capacitive load. So let's talk about why that is. Capacitive loads are incredibly rare. You can connect a synchronous motor in such a way that it represents a capacitive load. However, connecting the synchronous motor in that way is usually done to provide power factor correction for all of the other inductive loads. Inductive loads are what you are going to see the overwhelming majority of the time. All induction motors represent inductive loads. A synchronous motor could be an inductive load or a capacitive load, depending on how it's connected. But the simple connection is also an inductive load. So that's why we don't really talk about correcting capacitive loads, because it just doesn't happen.
Even though our power factor in the Y connected is lagging, it's still closer to one compared to the leading power factor. So I'm trying to, whenever you ask like why would we use one over the other, I was trying to figure out if lagging versus leading actually had an implication on which one would be first.
So, from the perspective of your utility, not particularly. So 0.95 lagging and 0.95 leading to them doesn't particularly matter because the efficiency is effectively the same. So they don't particularly care about leading or lagging. They just care about how close you can get to one. Doesn't matter if you go from leading into lagging or vice versa. The closer you are to one, the better.
Not thinking very good.
Okay. I don't think very clearly most days for what it's worth. Sam, you have a question? So I'll ask again. We've got 40 minutes. What do you guys want to talk about? What's confusing you in this material? What would you like to see more example problems of?
Like, I don't know why, but like, maybe it was getting adjusted at the beginning. My notes for when we first did this, I didn't take very good notes, and then I just worked a bunch of problems.
Okay.
That's all I did. So, I did mostly memorization, how to solve it. So whenever I get to these, it's like, I'm trying to grab something I don't have confidence to do.
All right, so do you want to work more problems from a circuit analysis perspective or a power analysis perspective?
Definitely.
Okay. All right, so I'm just gonna crack open this good textbook that I brought, and we're just gonna rip through some problems. Yes,
Bonus, the backbone, is that explicitly yes, or we're doing something about that?
no, so the bonus question for your upcoming exam will be what we cover on Thursday, which is power measurement. So this is all just, hey, we have these things, blah, 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 but we don't really understand where they came from. What we're going to talk about Thursday is using watt meters to measure power in three-phase systems.
First, our bonus is backbone.
Right.
You said you weren't explicitly gonna ask that, but we're gonna be next test, is that, are you gonna explicitly?
No, we're good. Yep. All right. So let's see. So I like this textbook because explicitly it gives you little lightning bolts next to problems that mean quote unquote they're hard. By the way, the third problem from the ICA was one of those light bulb problems. So just because this book thinks they're hard doesn't necessarily. Okay.
How difficult is it to make one of these problems and have?
Not hard. I mean, you just need to make sure that there's enough information provided, like all of the relationships are, again, as a jackass with a PhD, fairly straightforward. I know that you guys probably don't agree with that, but with enough practice, you will. Okay, so here's a problem from this book. So we have Load one has the following properties. 18 kilovolt amperes at 0.8 PF lagging. Load two, 8 kVA at 0.8 PF leading. On load three, we have 12 kVA at 0.5 PF lagging. We are told the voltage at the load, it doesn't explicitly say this, so I'm going to force this to be. So our line voltage at the load is 208 volts RMS. At 60 hertz, and we are asked to find the power factor of the source. So Trilon, how are we going to do this? So my preference would be for you guys to approach this incredibly similarly to how we approached things when we were dealing with single phase circuits. And by that, I mean, if we can calculate the complex power supplied by the source, then we could know anything about what the source is doing. So if we're looking for a source related quantity, doesn't matter if it's average power, apparent power, reactive power, power factor, complex power, all of those are buried inside of our complex power relationship. So how would we find the complex power supplied by our source? Yeah, absolutely right. Just the complex power absorbed by each load and add them together, 100%. Okay. So we know that S3 phase for our source is just going to be S3 phase for load one plus S3 phase for load two plus S3 phase for load three. Absolutely. So this begs the question, how do we find the complex power absorbed by load one, load two, and load three? And it's all going to be literally the exact same process because we were given apparent power for each of these loads, and we were given the power factor for each of these loads. So this one doesn't even have a curveball in it. So you've made a mistake. So you said 18 over 0.8. The reason why I say you're making a mistake is because we already have apparent power, so we don't need to divide by the power factor. We only divide by power factor when we have average power. How can we tell the difference between if we're given average power or apparent power? Right. So if we're given a quantity in volt amperes, it's definitely apparent power. If we're given a quantity in watts, it's definitely average power. So that's going to tell us whether or not we need to divide by our power factor. So for load one, that's just going to be 18 with an inverse cosine of 0.8, which is going to come out to be 18 angle 36.870 degrees kVA. What are we going to do for load 2? Effectively the same thing. However, we need to pay attention because our power factor for this one is leading. So how do we incorporate that piece of information into our mathematical expression? We put a negative sign in front of the inverse cosine to force that angle to be negative, right? So that's going to look like 8 kVA with an angle of negative inverse cosine 0.8. So that'll be 8 angle negative 36.870 degrees kVA. Load 3, same thing as number 1. Absolutely right, man. So 12 kVA with an angle of positive inverse cosine of 0.75. Comes out to be 12 angle positive 41.410 degrees. Adding those three results together, wind up getting 43.300 with an angle of 39.524 degrees kVA. So how do we get the power factor at which our source is supplying power under the assumption here that our transmission lines are of negligible impedance? Yep, so cosine of 39.524 degrees. Cosine of the angle of what I have stored as t. .771. Is this power factor leading or lagging? Lagging because the angle is positive. All right, so let's take this information and let's incorporate some of the stuff that we covered today. Let's say that we wanted to correct the power factor at which this source is supplying power to 0.9 leading. How would we go about doing that? So our ultimate goal is to find a capacitance value. Okay. We have our, Nick, were you raising your hand? Okay. So let's put this here, right? So now we want PF new to be 0.90 leading. So our equation for our capacitance generically is P three-phase old times tangent of theta old minus the tangent of theta new divided by 3 omega, and then the voltage drop across the capacitor squared. So I would argue that right now we explicitly know what theta old is. That is the 39.524 degrees that we previously calculated. Or I brought up the concept of power factor correction for this problem at all. How are we going to find the other pieces of information? So omega, what's that going to be, Sam? 120 pi, because our linear frequency was 60 hertz. So we just multiply that by 2 pi. Absolutely correct. So theta nu, how are we going to do it, Nick?
Negative.
Absolutely right. Because it's leading, absolutely correct. I'm just making a note here that I have that in my calculator as A. And this is in my calculator as T, so that when it comes time to solve for things, I know what variables to use. Okay, so we've got theta old, we've got theta new, we have omega, so we're missing our three-phase average power, and we're missing the voltage drop across our capacitor. Three-phase average power, we have enough information to solve for that. The voltage drop across our capacitor depends on whether we're dealing with a Y-connected bank or a delta-connected bank. So we'll sort that out in a minute. How are we going to get our three-phase average power? Average power of the source, right. So it is just, if I express this guy up here, luckily that I have stored in my calculator as T, in rectangular form, that would give me the average power and the reactive power. So P three-phase old is just the real part of S three-phase old, which is 33.4 kilowatts.
The total that we got.
Yeah, so the total that we got earlier, or S three-phase S, let's use the same notation so that it's not confusing. I apologize for that. So if we knew how much total complex power our source was supplying, the real part of that is just the average power. All right, so I'll leave it up to you guys. Do we want to solve for a Y-connected capacitor bank or a delta-connected capacitor bank? Is the voltage, right? So let's look at what voltage we have, okay? So we have a line of voltage. Okay? So does that mean, so because we have a line voltage, that means that we could use this voltage by itself to determine the delta connected capacitor value. And then from that, we could just multiply that by 3 to get our Y connected. Or if we wanted to calculate our Y connected capacitor first, we would simply take that 208 and divide it by the square root of 3, which is actually just 120 volts for this, give or take half a volt of rounding error. Okay. So do we want to do delta or do we want to do Y? Let's do delta because we don't have to mess with stuff. Absolutely reasonable, right?
Why? It doesn't work.
I figured it was gonna be some, no offense, asinine pun. Okay. So,
W-Y, like W-Y-E.
Just out of the blue. We still talk about it.
so I'm putting here explicitly that we're saying the magnitude of our capacitor voltage is 208 volts RMS, and we are assuming that our capacitor bank is delta connected, okay, because I didn't specify which one that we were looking for. In your homeworks and on your exam, I will tell you exactly if I'm looking for a delta connected bank or a Y connected bank. Okay. So now we would just literally put all of this information into our capacitor equation, right? So we're gonna have 33.4 times 10 to the positive 3. So that's just me converting my kilowatts into watts times the tangent of the angle of t minus the tangent of what I have stored in my calculator as A divided by 3 times 120 pi times 208 squared. I got 572.942 microfarads. I'm going to put explicitly here that this was C delta. If I wanted CY, what could I do? Multiply this by 3. $1.71 7188, so 719 millifarads. So you can multiply the whole equation if you wanted to. I'm just multiplying the last answer. It's 6 of one, half a dozen of the other. It's literally the same damn thing. So I'm too lazy to type all of that in my calculator again and just take the 3 out. So I'm just going to multiply the final result. Because as my mental strategy, I would find whichever one. So if I know that I have a line voltage, I would find the delta connected thing or the delta connected bank. If I know that I have a voltage measured from the line to the neutral or a phase voltage for a Y, I would find the Y connected first. Because that way I don't have to monkey around with that capacitor equation at all. And I know that once I find one, I can easily find the other by correctly either dividing or multiplying by 3, depending on what the case is.
So we assumed a delta capacitor that's near the 208 voltage. So if we were to assume the opposite, where it's the Y first, it doesn't change any of the other like delta or.
So it wouldn't change any of that. The only thing that it would change is because this voltage 208 volt RMS was specified to be a voltage measured from a transmission line to a transmission line. If we wanted to calculate the Y first, we would need to convert that to a voltage measured from a transmission line to a neutral terminal, which is just 208 divided by square root of 3.
Okay.
All right, so let's see if we can work another problem in the next several minutes. Let's see.
Instead of, two phase instead of one, or like one that's similar to problem two. Because it's not the same, it's not the same problem.
So that one will be too long. All right. So let's say I have the following system where I have a delta connected source. So this will be VAB, VBC, and VCA. I have a line impedance ZW. And then I have a Y connected load. Like so. Let's say that VAB is equal to 400 angle 0 degrees, volts RMS. ZW is equal to 0.3 plus J 0.2 ohms. And ZY is equal to 10 plus J 8 ohms. I want to figure out C delta if the power factor of my source needs to be corrected to 1. So this is tying literally everything we've covered for this three-phase analysis stuff all together effectively in one problem. So we've got some circuit analysis effectively on the front end that we need to do in order to be able to calculate the total complex power absorbed by our load and our transmission line network. And then we need to figure out from there what capacitor bank to put in delta in in order to correct the power factor of this network to 1. So this is literally every bit of material that we've covered in this module of the class, all in one single problem. So how are we going to approach something like this? So our ultimate goal is finding the value of that capacitor, right? Oh, and actually, I need to give you the frequency, or we're going to need that information later, so I'm just doing it. Right. So how are we going to find the total complex power absorbed by our transmission line network and our load? Let's start there. So 3 times the total complex power absorbed by one phase of the transmission line network, and then 3 times the total complex power absorbed by one phase of the load. Okay, that's fair. So how would we find the complex power absorbed by one phase of our load? Let's start there. Okay, let's break this up into bite-sized pieces that we can wrap our head around. Okay, like as it's presented to you, this seems daunting, and that is intentional. So ZW times ZY, ZW plus ZY, they're in series, so I think it's a reasonable. So let's use a single phase equivalent circuit really quickly here, and let's see if we can sort something out, okay? So my single phase equivalent circuit would be this guy right here, VAN. Here's A, here's N. Here's ZW. Here's uppercase A. Here's ZY. And here's uppercase N. So that's my single phase equivalent circuit. So I would argue that if we can find the complex power supplied by this voltage source VAN, that would be the same thing as the complex power absorbed by the A phase of the transmission line network and the load together. So how might we go about doing that? So this is a single phase equivalent circuit. So this is literally the crap that we were doing on the last test.
We have VAB, so I know there should be.
So, okay, so we have VAB. How do we get VAN from that? They're not. So the magnitude of VAN is the magnitude of VAB divided by the square root of 3. So that's just going to be 400 over root 3. And realistically, we could leave it as that. And I would argue that technically for our power calculations and all of that kind of stuff, we only actually need the magnitude to begin with. So this seems like a reasonable thing. Okay. So I firmly believe that we now have enough information to determine the complex power either supplied by our voltage source VAN or the complex power absorbed by ZW plus ZY, because they're the same quantity. Now that we know what the magnitude of that voltage is.
We do 400 over conjugate of DW plus E1.
400 root 3 squared over those two impedances added together conjugate. 100% correct. 100% correct. So the magnitude of VAN squared over ZW plus ZY conjugate the whole thing is going to be 100 volts RMS, excuse me, 400 volts RMS, 3 times, let's see, 10.3 minus J 8.2, and I forgot the square up here. I got 4050.996 with an angle of 38.524 degrees. And this would be in volt amperes. So that's the complex power absorbed by one phase. So how do I get the complex power absorbed by all three phases? Multiply it by 3. So S three-phase for our source is just 3 times SA is 12,152.989 with an angle of 38.524 degrees. Now, this is literally just a power factor correction problem. Right, so we're trying to find C delta. So C delta is going to be P three-phase supplied by our source times the tangent of theta old minus the tangent of theta new divided by 3 omega times the voltage drop across our capacitor squared. I'm going to draw our capacitor here in our delta configuration. Like so. So just as a heads up, what's the voltage drop across our capacitor? Same as VAB, right? Because if our source is connected in delta and our capacitor bank is connected in delta, it's just the voltage drop across the source. So 400 volts RMS, okay? So 400 volts RMS, okay? What's omega? So 100 pi. What's theta old? .524 degrees. What's theta new? So our target power factor is 1. inverse cosine of 1, which is 0. So the only thing that we need to sort out is what P three-phase for the source is, which is just the real part of that guy. So we're already ready to solve this thing. So I'm going to take the real part of what I have stored as x times the tangent of angle of what I have stored as x minus tangent of 0 divided by 300 pi times 400 squared. And I get 50.196 microfarads. Finished it for the class. I'll be done.